Okay, yeah, so thanks very much for the chance to present this here. I think it's really nice to have this other talk about the DEL-based or epistemic planning with implicit coordination just before me. Because the problem I want to tackle with this is exactly that in epistemic planning with DEL models, at least the standard crypto models, you encounter a state explosion problem. And a few years ago, in this 2018 paper that was mentioned, we tried to find a new data structure or a new representation for crypto models. And meanwhile, also other people have worked on similar things that might be useful for representing planning problems in a more compact way. So, and the main problem that I want to tackle are perspective shifts. So I will quickly go through what they are and why we need them for planning. And then the main two parts are about the symbolic methods, which I mainly developed myself, and also the succinct methods developed by François Schatzentruber and Tristan Chaillet. Okay, so a perspective shift is needed in an epistemic planning scenario, just like this famous doormat example here. Because agents have to take the perspective of each other. So in this case, it's not enough to just leave the key under the doormat for someone, but we also need to tell the other person that the key is there. So we also have communicating actions and things like that. And in order to reason about others, you sometimes have this state explosion problem, as nicely seen in Hintika's world here, made by François, that say if one agent here thinks about another world that this agent might have number 5, then this agent considers number 6, and so on. So in fact, this model of what is known as the consecutive numbers puzzle even leads you to an infinite Kripke model, depending on whether there's a bound on the numbers or not. So more formally, perspective shifts are defined as an operation on sets of worlds. So we have a set of actual worlds, which I will here call omega. And then the perspective shift for an agent I is given by all the worlds that this agent considers possible. So we close under that agent's accessibility relation. And in practice, then in a Kripke model with, say, these 4 worlds, this looks like this, that we say we have the actual world 0. And then if we close under the relation for agent A, then we would get the set 0, 1. So the local perspective of this agent would be given by this subset of worlds. And similarly for agent B, we would get this set of worlds. And then finally, we can also do nested perspective shifts. So we can think about what does A think, what B thinks, and these sort of things. And in this case, we would get the set of all worlds if we would have a nested perspective shifts, first doing the perspective for A and then that perspective for B. Now, the problem with this is that every time you want to compute a perspective shift, you in principle need to consider all the worlds in your model, or it depends how you have stored this set of worlds in memory and what sort of data structures you use. And then if you want to do nested perspective shifts as sometimes necessary for planning, the problem becomes even worse. So in a paper also by Rijfstek and others, and I think Thorsten Engerser was also one of the authors, they say that the most impactful limitation at the moment is the memory consumption of these epistemic states, because we don't really know how to maybe store multiple of them in a more compact way. So the goal of this work then is to say we want to find a compact encoding of what it means of this statement that Alice or another agent considers a specific set of worlds possible. And in principle, just representing this set of worlds would be easy, because in most of our models, we can ensure that we have what we sometimes call unique valuations, right? That you do not have 2 possible worlds that satisfy exactly the same proposition letters. And if we have that, then we can in principle just write down a formula, sigma, a Boolean formula even, that is true at exactly those worlds. And that is also the encoding that the 2 methods I will present here are using, that we identify a set of worlds with a formula, a Boolean formula that is true exactly at those. And the question then is, if we have this to represent a set, how can we still do a perspective shift? So suppose I'm now given not the set of worlds, but I'm given the formula. How can I go to another formula that describes the set of worlds considered possible by that agent? And in order to do that, I also need to know the relation of the agent, but now also this relation will not be given as a set of pairs of worlds as it's done in an explicit Kripke model where we have arrows between the dots, but I will also need some more compact encoding for the relations in the model. And there are 2 ways, at least that I know about. And the first one that I want to mention here is the one that I mainly developed during my PhD thesis, but it's also been known in the model checking literature on temporal logics before that. And the idea here is that we replace Ri with observational variables. So this is the idea that instead of saying agent I cannot distinguish these worlds, we just say, okay, agent I observes whether the variable P is true or false. And this at least gives you an encoding that works for S5. If you want to do weaker logic, so anything from K to KD45, then you can also do this without observational variables, and you can instead use Boolean formulas over a double vocabulary, and then the same relation would look like this, that you say the epistemic relation for this agent is described by this Boolean formula. I also have to say I will use a lot of Boolean formulas on my slides here, but in the actual implementation, we then use binary decision diagrams, which are a very nice data structure that has been used in other model checking work as well. Now, the other approach is not to use observational variables or these double vocabulary formulas, but so-called mental programs, and they were mainly developed by Charrier and Schwarzentruber. And in this case, they are sort of dual to observational variables or these formulas that I use, because what Breston and François do is basically they write down a program of the things that you're allowed to change. So you don't write down the propositions that you observe, but you write down steps that you can do in order to reach another possible world. So if we only have the propositions P and Q, then this example would look like this mental program here, and that's a variant of PDL. Okay, so now the rest of this talk, depending on how much time I will still have, is how to compute sigma I, so how to compute a formula that describes the epistemic perspective of an agent if the relation for I is given by one of these two symbolic representations and not as an explicit relation on sets of worlds. So as the first thing about the symbolic worlds, I can probably not describe the whole idea here behind knowledge structures, but what you can think for now is that they are basically a new data type or a different encoding of Kripke models. And you can believe me that for every Kripke model, there's a knowledge structure and vice versa, and that you can interpret the same kinds of formulas on them. And intuitively, a knowledge structure encodes an S5 Kripke model as follows, that we say we have a vocabulary and then a Boolean formula which says which states exist, and a vector of observational variables, which are subsets of the vocabulary that are observed by each agent. So a very simple example here is that the Kripke model we've already seen on previous slides is encoded by this knowledge structure where we say, okay, we have two propositions. All the combinations are allowed. So the Boolean state law here is just the top formula. If I would write here P or Q, then for example, the world 3 would not be there. But here I have all the 4 possible worlds. And then I also say that agent A observes variable P and agent B observes variable Q. And this induces the relations in the explicit form in a Kripke model. And finally, we can mark the actual state using a Boolean formula where here we say, okay, P and Q must be true for a world to be actual. And this also naturally gives you a way to define multi-pointed models because we can now put a formula that is satisfied at more than one world. Now to do these perspective shifts on these encodings, I now found this definition, and well, it's actually not hard to come up with it, but it's a bit more a mess of notation and a bit tricky to prove that it actually works in all cases. But the main idea is that you can do operations on these Boolean formulas that exactly correspond to the definition of an explicit perspective shift. So in the explicit perspective shift, we first say, okay, we want all those states which are part of the model, which were in W. And for this, in the symbolic version, we use theta, which was this formula that tells us which states exist in the model at all. Then in addition, we want those states that are reachable from the set that we were already given. So before that, we were given the set omega. And now, before we did the shift, we were given a Boolean formula sigma. And then I want to have all the states that are reachable from there. And instead of the explicit accessibility relation in the Kripke model, we now use a Boolean quantification here over all the variables that the agent do not observe. Okay, so the result in this parentheses here will be a formula. And then what this Boolean quantifier in front of it does, it says it's going to build at least semantically, a big disjunction where all the propositions occurring in the formula which the agent does not observe can be flipped to top or bottom. And then actually in practice, I don't want to do this syntactically, but I do this as an operation on binary decision diagrams. But the main intuition you should get here is that an agent considers all the states possible in which those truth values that he did not observe are changed in either way. And then the result of this is again a Boolean formula. So I'll quickly show an example. So here on the left, we have a Kripke model, and on the right, we have a knowledge structure, which are from the previous examples. And then here, this shift from, say, the set only including 0 to the set containing 0 and 1 would be given by this Boolean quantification, where we remove the Q from this conjunction, because Q is something that the agent does not observe. And analogously, we would get we would remove P from the set and only get Q for agent B. And then a theorem that you can find in the paper is that this exactly matches the explicit definition. Now, a side note that I will probably jump over in the interest of time is that you cannot just do this for S5, but you can also do it for K. Of course, it's a bit of a discussion whether this makes sense and what a perspective shift in weaker logics even looks like. But at least formally, this can be done. And here's also an example in the slides in case you want to look at the recording later and stop it there. Okay, now the second method is not using these knowledge structures, but it's instead using mental programs. And this is the idea that we encode not just a set of propositions that an agent observes, but we write down a program in PDL style that allows us to change the truth value of atomic propositions and then combine these changes to reach other possible worlds. So here's an example of the mental program semantics, which say, okay, if you are at a state where, say, only Q is true, and then you change P to true, you would reach a world where P and Q are true. And there's also a discussion about which operators you actually need and whether you need an inverse and things like that. But I'll jump over that. You can look in the paper. So now what Succinct Del, or this work by Tristan and others, is doing is that for each agent, we now don't have a relation, but we have one of these mental programs. And again, now the question would be, if I'm given a formula, a Boolean formula describing a set of states, can I apply a mental program to a formula to get a new formula that describes the resulting set that would be reachable? And you can essentially do this by recursion. Also, none of these definitions is really surprising. For the other operators that sometimes are added to mental programs, it's a bit more difficult. And depending on which operators you want, also the translation is maybe not the most efficient or not polynomial anymore. But for these operators shown here on the slide, I think it works very nicely. And then I can show you the same example for this. So again, here on the left side, we have an explicit Kripke model. But now, to make it a bit more interesting, it's no longer an S5 model, but we have also one-directed arrows here. So in this model, in fact, agent A has a false belief that this is the actual world. And in a succinct model, this would look as follows, that in the mental program for agent A, we can see that the propositions P and Q must be true for that agent to have to reach a world. And then we can also do now the perspective shifts for these agents by applying the mental program to the given Boolean formula. So here in this case, if we start with the actual state, not P and not Q, and then we apply the mental program for A, we would result in the Boolean formula P and Q. Or at least syntactically, we might not directly arrive at that formula, but then an equivalent formula to that is P and Q. And again, if you want to implement this, it would probably make sense to not use syntactic Boolean formulas, but another thing, at least normal forms, or maybe also binary decision diagrams. Okay, so to give an overview of this, I basically try to translate this explicit definition of perspective shifts to the symbolic and the succinct representations for Del. For the symbolic version, there are two variants depending on whether you want to use K or S5. And actually, what I don't have time to talk about is that you need even more definitions, because you not only want to do this for the Kripke models, but you also want to do this for the action models. because also when actions are executed, there might be different observability for the different agents. So also for the action models with pre and post conditions, you want to have a notion of what is the perspective of another agent. And both in the symbolic and the succinct framework, there are also compact encodings for these action models. And also on those, you can define the perspective shifts directly without going back and unraveling them to explicit action models. Okay. Now, what I'm also working on is adding all of these things into my model checker for Dell. So SmackDell is a symbolic model checker for Dell, which contains already updating with action models with or without factual change, and it covers S5 and K. But it doesn't have a lot of planning functionality yet, and it's work in progress to add these perspective shifts that I've now defined to this. And then eventually, of course, I also will have to add search functions for this. And there I'm hoping to also get a lot of inspiration from others, maybe also from the previous talk. Just one thing I wanted to show, so what this actually looks like in the implementation is that there are, so the implementation is in Haskell, and there's now a function that is called as seen by, and this is applicable to both states and to updates. So then you can write down something like updating a pointed model with an event under the perspective of this agent, and then after taking the product update, shifting again from the perspective of another agent. And that would translate naturally to this short piece of code here. Okay, and I think I will skip over this in the interest of time and move to my summary slide. Thank you very much.